Hello everyone, I'm going to try to make another video for you guys. We're going to talk about elimination reactions. And if you remember when we had the substitution reactions, we always wound up with something that was very similar. In our elimination reactions, we're always going to wind up with an alkene. So we're going to still have that R leaving group, but instead of having the R nucleophile, we're going to have H leaving group plus an alkene. So let's talk about what that looks like. And let's look at an example. And I'm going to start with the E1 reaction. So if I have, and I'm just going to put CH3, 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 and a bromine here. And this is going to be SN1, and I'm going to use a strong base or whatever type of base, NaOH. Oops, let me make that neater because I can write neater than that. NaOH, right? Strong base. My bromine leaves. The first thing I'm going to do is have this carbocation. And I have two options. I could have a nucleophile come in and attack, or what happens once I have a carbocation is the hydrogens right next to the carbocation are more acidic. So if I have OH come in, boom, and then I will form a double bond. So that will go to boom, 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 boom. And you notice I went from an alkyl halide to an alkene. Let me do that one more time just to kind of show you what's going on. Erase over here. So in the elimination reaction, and I'm going to draw out and I'm going to write the Lewis dot structure for you guys because I think that will be a little bit easier to see. Carbon, C, C, H, H, H. I'll put my bromine here, and carbon, hydrogen, hydrogen, hydrogen. Just like SN1, the first step of the reaction is for the leaving group to leave. And I'm just going to say I have a base in here. Again, we'll start with NaOH. Everybody kind of sees that both as a base and a nucleophile. First step, my leaving group leaves. So what's going to happen is I'm going to get C plus C, H, 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 C, H, 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 C, H, H, H. All of these hydrogens, we call them beta hydrogens. They're next to the carbon we're talking about. So these all become more acidic because if I take one of them off, let me make this back to be neat and tidy now that I made it a mess. But if we go back, oops, that's C, H, 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 C, H, H, and H. So now I can take off one of these hydrogens, just like an acid-base reaction. The hydrogen is going to give the electrons, that bond is going to go and make a double bond, forming C double bond CH2, CH3, CH3. And in this case, when I'm talking about tert-butyl bromide or bromoterbutane, or if you want to do the IUPAC, it would be 1, 2, 3. It would be 2-bromo-2-methyl propane. It doesn't matter. We would always get the same product. But if we have choices, I'm going to talk about how we decide what is the most stable alkene. And notice this alkene wouldn't have cis or trans, right? Because these two are the same and the hydrogens are the same. So I would not have a cis or trans or easy, whichever one you want, diastereomer. Pause for a moment, and hopefully you guys can hear me.